This video is going to show you how to work independent t-tests for the 6 steps of hypothesis testing from the Nolan and Heinzen Statistics for the Behavioral Sciences. Alright, so what I have done is come up with a couple of examples to show you how independent t can be worked through our 6 steps using both MOTE and SPSS. If you need to know how to work either one of those, you can go watch the videos for those, and including how to download MOTE. So, a record company is interested in the difference between 2 different artists. So this is a big clue. It's independent t. If it's 2 different groups of people, whereas dependent t is the same people twice. Okay. So given the ratings, are they significantly different? So we got 0.05 as our criterion. So you'll notice that as we go, you get less and less setup of stories because it's just use the numbers we have because we don't have any of the population numbers. So here's the data if you want to enter that into SPSS or your favorite program to calculate the means, and I'm going to show you the numbers I've already run. Okay, so I got 2 different artists. Now here's the tricky part. In most of these problems, they're going to give them to you, and it looks like dependent t because they're laid out next to each other. Right, so it's very tempting to enter this in column 1 and column 2. Don't do that. Bad. No, stop. Remember that this actually needs to go like this, where you have all of this data, number, and that is the rating. And then you also have a column that is their group or their artist number. Okay, so it's like 1, 2, 1, 2, or 1, 1, 1, 2, 2, 2, etc. So, be sure you don't put them as column 1 and column 2, and instead you put it as all this data and then what group they're in. Okay, so that's the part where you can get screwed up. Because when you watch the video for independent t, you'll see that you need to have a grouping variable. Otherwise, it would be tempting to run this as dependent t, and don't do that because that's incorrect. Okay. Alright, step 1 here is that the DV is scale. They didn't tell me a whole lot about these ratings, but they kind of look like 1 to 10, maybe 0 to 10, so they're likely at least interval. So I would say, yeah, they're interval. Okay, to check. 2. Random selection. I have no idea how they got these ratings. So I'd probably say probably not. Because I wouldn't have access to the entire population, which is all the people who've listened to these artists, so I don't know. Probably not. Random assignment. Well, again, they didn't tell me a whole lot about the study, but probably what we could do, if you think about it, is have people listen to the artist and then rate them. And I could randomly assign them to which artist they listen to and then rate them. Now, if I got these from, like, Facebook, that would not be random assignment, but if I put them in a study where I could control who they were rating, it would be random assignment. So we could do it, but I don't know if they did in this study. And then 3, is it normal? Well, I didn't really count how many people there were, but I think it's less than 30, so it's questionable. I would probably say no, and I'm not sure. I can't assume it anyway. Okay? So same step is, for step 1, what are the assumptions? Alright, step 2. This is where it gets kind of hairy. Whoop. You're going to put level 1. I keep writing level L just for fun. Here we go. Level 1 versus level 2. Our DV in this example is ratings. So you just listed 2 groups. Artist 1, artist 2. And what I tell you to do is however you put them into SPSS, whoever you made level or their value label as 1 and this value label as 2 or 0 and 1 or 87 and 4, whatever you want to use as value labels, make whoever's lowest this left side over here. Okay, so research and then null. So I don't think we really picked, did we? I am spelling out of control today. All right, so let me back up for a second. And it says, are they significantly different? So I didn't pick a side. I'm going to do a two-tailed test. So erase these things. They don't matter. not equal to, and equal to. So I haven't really told you who I expect scores to be higher. And so I'm just saying, are these two artists different? Okay, so that is a two-tailed test, and we're going to use 0.05 here in a little bit. The first thing you want to use is this box. Now, what I'm going to do is stack that information. So I've got artist 1 here and artist 2 here. Now, if you enter value labels, they'll come up over here. If you don't enter value labels, it'll be whatever numbers you picked. So let me list the means. So for the first artist, I got 3.13. For the second artist, I've got 6.5. So clearly this one is higher, just mathematically, but is that significantly different? So the numbers you want to use are these three. Don't use this one. Let's also list the degrees of freedom. So it's n minus 1, so 7. Degrees of freedom over here, n minus 1. Okay, oops, so 7. And now, if you were going to calculate S pooled by hand, which I don't recommend, you would use these standard deviations. So you could list both S's. But what I want you to do is to use these programs so you don't make a math mistake. And so what I did, if I skip a step, is I plugged it into Mote. And so I used this information, these three here. So I'm going to skip this slide for just a second. And I entered means, standard deviation, n. So it's the same rule as dependent t, is you have to enter the means and some form of standard deviation and then n. It will calculate these numbers for you. So these are not important for what we're doing today. But they should match this. So it's 0.61, 0.87. So they're in there correctly. It'll actually give you t. I must have clicked on it so you can't read it, but t should match. It gives you degrees of freedom total. So you need df total for step 4. But remember, this is pretty easy. It's going to be df1 plus df2. That's not the hard part. So 7 plus 7. Okay. What we're trying to get to that's kind of hard is pooled standard deviation. So S pooled. Remember, the formula for this is pretty gross. So it's degrees of freedom 1 over df total times the variance for group 1 plus degrees of freedom 2 over df total times the variance for group 2. Take the square root of that whole bad boy. Ew, so many places that you can make a math mistake. So instead, if you enter these numbers and these numbers into Mote, you can get pooled standard deviation right here. So it's 2.12, and that's already with the square root taken. Okay. Why do I need that number? Well, you need it for Cohen's d. So we're going to come back to Cohen's d here in a little bit. All right, so 2.12. It also gives me the pooled standard error, so 1.06, but I get that information here as well. So for the purposes of step 3, this box gives you standard error of the differences. It's a very similar name to dependent t, unfortunately. Okay, and that's here. So 1.06. But if you wanted to use Mote for this entire step, you could. So what do we got to have for step 3 to get full credit? You need the means. So there's going to be 2 of those. You need degrees of freedoms. There's going to be 2 of those. You need S pooled, which I just showed you on the previous slide, and SM difference. Okay. This one's for effect size. This one's for T. Okay, and this is for T as well. This is for step 4. All right. So a couple different places you can get it. So here are the means. You can get standard error from here, or you can calculate the whole thing with that mean table, right, in Mote. Okay, so step 4, I got my degrees of freedom is 14. And then I'm going to go p less than 0.05, and I did a two-tailed test. So here's my two-tailed side, 0.05, degrees of freedom is 14, all the way down here at the bottom. It won't let me draw. There we go. So 2.145. So the answer, is plus and minus 2.145. I'm going to draw that on step 6 real quick. So both sides, 2.145, 2.145, this one's negative. Everything out here would be reject. Everything out here would be reject. Everything in here would be fail. No, bad. Okay. PowerPoint is got a mind of its own. All right. So for step 5, we want to calculate t. Well, t is technically mean 1 minus mean 2, whatever order you put them in, divided by standard error of the differences between means, not the difference scores. And so it gives you mean difference here, but standard error here, so that's how t is getting calculated. So in our case, it's negative 3.185. And would I reject? So the big thing about this is don't look at Levine's here, that's a different class, and don't look at the bottom line. So you really want to use this top line. So I've got negative 3.185, which is here. Got my little car, vroom, vroom, and it crossed the finish line. So I would reject the null. There is a significant difference between artists. So when you reject the null in this step, what you want to do is back up to where your means are, which is quite a ways here, and then tell me what happened. So if you could say there's a significant difference between artists, most people are going to look at you and be like, yeah, so what? Who scores better? Well, artist 2 scores higher. So I would say that artist 2 had a higher score than artist 1 because they are significantly different. All right. Let's talk about confidence intervals. Now, traditionally, what most researchers do is they create 2 confidence intervals. So they take the mean of artist 1 and the mean of artist 2, and they say, here's the confidence interval for each mean. Do they overlap? What the book in this case suggests is to take the mean difference between the 2 and create a confidence interval, so this thing, around the mean difference. Okay. So I tell you that traditionally most researchers create confidence intervals for each mean separately, but what your book is going to suggest is to do the the mean difference. So if I was to calculate that by hand, it would be 3.375. Right, so this is mean diff, just like dependent t, plus and minus t critical for a two-tailed test, which we already figured out was something, 2.145. Okay, times standard error, so 1.06. That's a lot of math though, so I'm going to just use this. And what I would do is look and see if this confidence interval crossed 0. So it is 0, because remember we're still assuming mu is 0. The difference between the two is greater or different from or less than 0. And it's not. So that's why I would reject the null, is because the difference between the two does not include 0. If it did include 0, what you're saying is that the population mean could be 0, which means that nothing happened. All right, now, I've kind of already looked at this, but for effect size, remember you got to enter means and standard deviations and at least n. You can enter the standard error too, but it will auto-calculate if you enter those 6 in this example. Then we're going to come over here to Cohen's d. So it's negative 1.60 if I round up. Oh, no, 59. So d. Now, how's that calculated? What it's doing is it's taking mean minus mean, 1 minus 2, divided by S pooled. And so that's why we spend so much time getting S pooled, is because it's part of Cohen's d over here. Unfortunately, you have a cute little program that'll do it for you. Yay! All right, let's do one more example. So we're going to take those same artists, and now we know that artist 2 is more popular, but who is selling more albums? So we got R&B versus pop, and we're still going to use 0.05. So one of them is more popular than the other, but who's selling more albums? Because that, to me, is where the money's at, right? So here's the data. I got my R&B and my pop. And remember, it's set up next to each other, but what you actually want is sales, a sales column with all your numbers, and then an artist column with either pop or R&B out here to the side for each person. Because remember, each person has to have an indicator of their dependent variable and an indicator of their independent variable. Okay, so what are my assumptions? First one, is the DV scale? Oh, yes. It is ratio because I could sell 0 albums. That would be bad, I guess. To check. Can I randomly select? Probably not, because this is like the number of albums that they're selling, so I can't really randomly select. Nope. Can I randomly assign? I can't like give the R&B artists sales to the pop artists, so no. So can't really do either one of these. So that's a quasi-experimental design where I can't change those things. And is it normal? I haven't looked at how many people there are, but let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because I like to make up examples with 10 people, so there's only 20 people, and it's less than 30. So I can't assume normality. So no, I'm not doing so high. The only one I have is the one I absolutely have to be able to run this test. All right, step 2. Let's list our 2 different groups. Our DV is sales. So we're going to do R&B versus pop. And then R&B versus pop. And I'm pretty sure in the example problem, I didn't say who. I said who is selling more. So R&B or pop. And I didn't pick a side. So I went with a two-tailed test. And a lot of independent T ends up being a two-tailed test because you're comparing 2 different groups of people or 2 different groups of things, and you're not totally sure which one should be better. Now, every once in a while you'll have an idea, like, I think this should be better, but that does not necessarily mean that you would always know. Right? So, for example, in my research on statistics, if I have an honors class and a regular class, I should expect the honors class to have higher scores because that's the point. But in this particular example for these 2 types of artists, I don't have a side. All right, now let's list the important statistics here. So remember, these are the numbers we need. Don't use these. So we're going to list the mean. So the R&B is selling 160 versus this other mean. They're selling 148. So this one is higher, but is that statistically higher? And then the 2 degrees of freedom. So 9 and 9. We're going to use the standard deviations to calculate all those other fancy numbers. So I'm going to move on. So I need, this one is going to have standard error of the difference. So SM diff. And you'll notice how big it is. That's because the scale on this one is much larger. I can also list DF total from here. That's really for step 4, but it won't hurt you. So here's 18. Okay, so what we need is S pooled. So remember that you have to enter the means and standard deviations and N here to be able to get that. Then your T values should match when you have the right view and not where I have typed in mine. Your degrees of freedom should match, all that jazz. So S pooled is 101.66. Okay, we're going to need that number for Cohen's D, so that's important a little bit later. The next thing we're going to do is come up with a cutoff or critical score. So this is how far we have to go. Our degrees of freedom is 18. So that's DF total. And then we use 0.05, and I had a two-tailed test. So that means it's going to be plus and minus. So let's look at our table here. So I'd kind of cut off the top, but here's two-tailed test. Here's 18. Here we go. So 2.10. So 2.10. Perfect. Now let's write that down in step 6 real quick. So I have both sides, 2.10, 2.10. Right, so out here is reject. This is fail to reject. Out here is reject. And let's see how far our little car gets. Ready? So this one's negative, by the way. So step 5 here is the actual calculation of T. So remember, don't look at this. Don't look at this. Look here. So T is 2.264. Because remember, that's mean 1 minus mean 2. So R&B minus pop. Divided by standard error of the differences between means, which is this thing. So we had basically 12. Here's the mean difference over 45. So we didn't even really make it off of 0. Our car just went kaput really quickly. 0.26. So I would fail to reject the null. one artist is not selling more albums than the other. They're pretty much equal. For the confidence interval, I'm going to use this out here. So it's the confidence interval around the mean difference. So this study, what would I expect the population mean to be? If the mean difference is 12, it could range anywhere from -83 to 107. There's a huge confidence interval. So that means we don't have very much precision going on. We want confidence intervals to be kind of small, with the caveat to remember that it's based on the scale of the data. So 1 to 5, a small confidence interval for that, it's going to be pretty tiny, but when you have data that runs into the hundreds, confidence intervals can get kind of wide. Okay? So it would be -83 to 108, essentially. Okay? And then the last thing is effect size. So remember that D is mean minus mean over S pooled. That's why we spend so much time getting that number. So it's here. And D is equal to 0.12, which is really small. So I would say that not only is there not a significant difference between the two, and if you look at this confidence interval, it clearly crosses 0. So remember, if the 0 is in the middle, or 0 is in the confidence interval, you're not likely to reject the null. With a small effect size, that adds more evidence to me that there's really nothing going on. There is no difference between these two artists, and the effect size is kind of small. So all of that together is independent T, the 6 steps of hypothesis testing with effect sizes and confidence intervals.